All right, great. Let me just do a quick sound check. Chris, do you hear me?
Yes, I can hear you.
All right, fantastic.
Can you hear me okay?
All right, I think we're good to go, right? Hello everyone. Welcome to series of industry invited keynotes. We have three eminent speakers: Chris Galliano, Arpan Pal, Pramod Bajate. After whom we'll have Professor Ellen Zagora delivering her keynote from Georgia Tech. Our first speaker is Chris Galliano, who is the Chief Technical Officer of Skymount Medical Group. He has a very distinguished career that spans the US military as well as enterprise cloud systems. He's a veteran of the United States Navy, and he's been through various missions, including humanitarian missions in Indonesia and Sri Lanka, where he won the humanitarian medal. But his current interests are broadly in health and in enterprise cloud systems. So his talk today is titled Architecting and Managing Secure Enterprise Cloud Systems. So I really look forward to your talk, Chris. Over to you. Thank you so much. You're muted for some reason.
Okay.
Are,
All
are,
right.
are
Well,
you able to share
thank
your
you.
slides, if any?
Yes, yes. Okay. Well, thank you so much, and really appreciate everyone's time here today, and thank you to the COMSNETS group for inviting me, as well as my colleague Dr. Supratik Mukhopadhyay. I really appreciate the opportunity to be with you here today. We really wanted to discuss and discuss my experiences and provide some insight into what goes into securing a cloud. And the title of my discussion today is called The Never-Ending Ambition. As you can imagine, this is an ambition, it's a goal. We never quite achieve the ultimate goal in end state, but we have some techniques that we hope will finally move us there within the next year, the next decade, through this year as automation and AI and model-based systems engineering continue to come to the forefront. Just wanted to start today with some of my background.
I don't know. I feel like you're sharing slides. We don't see slides if you are, in case you are.
Okay, let's see. Can you see my screen now? Let's see, one sec.
We see you, but we don't see the slides. And we hear you fine.
Okay, okay. Let me click on here.
I'm going to have one of the volunteers to guide you through it.
Okay.
So there's arrow button in the middle. You can click on it to share the screen. Right next to the mic button.
Okay.
Yeah, you can just. Yeah. Thank you, sir.
Yeah, we're good to go.
Okay.
We're good to go.
Okay. Okay.
Sorry about that.
Oh, no problem. So appreciate being with everyone here today. I really hope I can make it in person and hope to make it in person next year. But have made this presentation and hopefully it provides some insight into the past, present, and into the future. A bit about my background. I really started early on with distributed computing and developing cloud-based systems for the US government. I was one of the early co-architects assigned to what's called the Navy Enterprise Data Center, which was within the Navy Marine Corps intranet. At its time in 2006, we were servicing 700,000 concurrent users and was one of the largest intranets in the world. My work there started in 2016 and continued through 2015, where we did NEDC consolidation and consolidated the Navy data centers from over 100 data centers down to 3 enterprise data centers, which went into the NEDC cloud model that we had developed. After this endeavor, I really started working with the academic community, which is where I met my colleague, Dr. Mukhopadhyay at Louisiana State University. We really started doing research in the space since 2015, but I got called back to start to work on a project called NATO ITM, which was the NATO IT modernization and consolidation of the NATO networks, over 20 countries into a single integrated cloud infrastructure network, and had been a part of that project and program from 2016 to 2018. So combined, these are two of the larger defense clouds in the world. There are others, but in terms of my experience, I had a direct hand in both doing the initial architecture, and of course, if you build it and you can describe it, you now have to defend it. And so security was always a primary goal in both of these endeavors. So this is really what it looked like when we all started. I call this the pre-cloud architecture, commonly or what we call the spaghetti diagram. As you can see, this is a series of legacy infrastructure that's been bolted on over the years without what we call an enterprise architecture view. Systems from the 1980s, systems from the 90s, the 2000s. How do they integrate, and how do they seamlessly provide services, and how do you secure these services with so many disparate systems running concurrently? If you're in the cloud space and in large enterprise architecture systems, whether it be Fortune 500 companies or governments, this is the mess that we've inherited. And although we didn't create it this way, this is what we have to deal with. This is the reality. And the result is there's dozens of ontological conflicts. And how can you run computation across all these systems? If you come from the very, very new school and we're part of startups or acquisitions of startups, this is less of a challenge. But when we're talking about enterprise services for major organizations, this is one of the primary challenges. And so this is what we're dealing with. This requires extreme architecture rigor. It's very resource intensive to secure, and it's very difficult to run computation across all these systems. So this is, I just wanted to upfront show this is the dynamic that we're working with. And so therefore we're under attack. There's new malware generated every day at alarming rates, and legacy security systems struggle to keep up. So these are what we call threats. There's viruses, worms, Trojans, spyware. There's millions of code packages out there, and of course thousands, if not tens of thousands, are developed of new malware packages are developed every single day and into the wild. So as you can see, with all of these threats being live and ever evolving, and with malicious actors continuing to develop them in new ways, we have to be ahead, and we have to have a superior way to both identify what it is and identify a countermeasure to what the thing is. And so this has been the challenge of the cyber industry for the last 20 years. And we hope to share with you today a way that we can now use automation and standards-based modeling to describe these things in a computable format to enable automation to take us to the next level over the course of the next decade. Okay, so in many cases, when we built the clouds, and most Fortune 500s will echo the same, a lot of the mess that existed in the legacy land, we didn't really do pure application rationalization and database rationalization to minimize and create a standard as we went into the cloud. I think back in 2010, everyone was so jazzed just to get into the cloud. We didn't put in the work up front to rationalize this mess when we went into the cloud. So in many cases, organizations took the same legacy mess, put it into the cloud as is, but didn't fix it as they went along. And so as we look back, apart from the race to the cloud, the engineering that should have gone into cleaning this mess up, which we didn't because we had to make milestones, is now still having to be dealt with. And so this is, again, the legacy mess that we still have, although it's not in physical server infrastructure now, it's in cloud server infrastructure. A lot of it has changed. There are tools that are helping us enable this, but in terms of the very large enterprises, this is still the case. And so again, it's hard to run computation across all the system, even if it is in the cloud. And so therefore, what we have to do now is we have to look at a way to untangle this mess. And I think model-based systems engineering, the unified architecture framework, and the hope of the new SysML version 2 standards are a way forward to help us achieve it. So what I tell everyone that I meet, your architecture is probably not secure unless you had the opportunity to build it from scratch and know where your vulnerabilities and your risk profiles are, and can map operational views to failure. It's very difficult to confidently say 100% certainty that your architecture is secure. This is largely due to a lack of the in-depth knowledge of one's own IT infrastructure. We have diagrams, but are those diagrams in proper computable standardized models? We often get a false sense of security from existing network defense products. You go to the trade shows, you go to the cyber trade shows, you walk the floor, you may see 5 to 10 things that are really novel, but there are hundreds of systems out there that are bought and sold every day because they have a nice user interface. But do they offer the context that you need to do something such as mission impact analysis or business impact analysis? And then lastly, I would say there's too many logs that look at what happened post-mortem, not enough analytics to show cause and effect, and to a degree of certainty that we can simulate into the future. So if something does happen, can we predict what's going to happen on the mission or business side as it's happening live or even in advance? So I would say post-mortem analysis versus future mission impact analysis is largely the missing piece in lots of the industry tools nowadays. And so back to the point, a lot of the systems that we've tested and prototyped, they tend to be superficial in scope. It looks like they're creating value to the organization, but can they actually mitigate a risk either in real time or in advance of a threat? So that's one question. And so since many can't, I often say that they're superficial in scope. The other point that I want to reiterate is most cyber systems right now, because they can't compute mission impact analysis, they can't give you a true cause and effect of an outage. And so this is something that's going to be very important in the future, and something that would be very beneficial to the future clouds if they can offer this as a capability. And then lastly, even the most sophisticated systems can look at known malware threats, but many of them can't look at new binaries and unknown unknowns. And so this is one of the major flaws in enterprise security systems, is they can look at things that are in the wild, things that are seen before, but can't really do much with new malware incursions. And so these are all things that need to be addressed as we both do design and defense of the future cloud. Okay, so this diagram here is very important and really moving into the cornerstone point of the presentation here today. If you look up at the slide, there's the 80-20 rule. And so what we've observed, and this number is increasing daily, but with up to 50,000 new malware packages deployed every day in the wild, this is a tremendous amount of manual effort that it's very hard to have individuals work on this. So this is where the power of automation and AI and model-based systems engineering can really help us. What's really happening is when these malware packages are generated, they follow the 80-20 rule, meaning they look at a sample of a pre-existing malware, and oftentimes they're too lazy to develop something from scratch. So what they tend to do is they change 20% of the malware package and keep 80%, but that 20% variability of the new package is what creeps through the enterprise security and perimeter defense systems. So this is the trend that's been going on for a long time. One former government contractor estimated up to 50,000 new definitions every 24 hours. So if you can imagine, all these new packages, all these new viruses are flying. We have a hard time dealing with Omicron and Delta, but if you can imagine 50,000 new malware packages per day, this is very hard and labor intensive to keep up with. So we feel that the power of automation and coming up with a new way to model these malware representations, where we can identify the 80% and the 20%, will allow us to both take that and close the loop and see what has changed, have confidence in what has changed, and then have confidence in how we can defend our cloud, having this knowledge base. So this is a very important knowledge base to address. And if you can start here, this is where your threats are located. So this is an important kind of a threat repository approach. So what we've done is we've, with 50,000 per day, that's so many binaries. How can any analyst look at all 50,000 every day, much less look at the nuances of the binaries of what's changed? So what we've had to do is we've got to automate the process to take these malware binaries and go from malware binaries to creating models. And the best format that we know to use is use UML constructs, and also a standard called MIC, which is the malware attribute enumeration characterization standard. It's available on GitHub, so it is open to the public. And what you're seeing here is simply a malware package that came in as a binary. We ran it through the model generator. We modeled it on the fly in near real time, and the output is a complete breakdown of the malware characteristics, which tell us its capabilities, its common taxonomy, and then we can look at different zones to see what we've seen before from this package, or what's new, or what's novel. Maybe 50% is new. Maybe only 2 of these boxes and characteristics are new, but the rest we've seen before. And so the key to this is not only an analyst's ability to look at the malware and break down with full descriptors of its capability, but when we write this binary in model form, when we do the write into the database where we save these, we have full metadata management on the malware, and the recall and the quality of the analytics in the long term are far superior than just looking at binaries, which humans have a very hard time looking at. So I just want to stop on this point here. This is a very important breakthrough. If you can model the threat, and model the threat through automation using SysML v2, UML, Unified Architecture Framework, UPDM standards, and express the data with full representation of the capability, the ability to recall, the quality of analytics goes way up. So this was a major breakthrough that we've made in the last 5 years, and we're looking to move this kind of approach into the future with the advent of AI becoming more and more operational. So this is what we're really looking at the end of the day. There's a direct correlation between these three things, and I put them in red, green, and yellow. We have the whole cybersecurity model is based on threats, risk, and vulnerabilities. If you can model the threat, the malware or other versions of the threat in the same language as your enterprise business systems and architecture, and then also model your risk, your threats, and your vulnerabilities in the same construct, then you have a model of the threat. You have knowledge of your vulnerabilities. They could be endpoints or gateways. And therefore, because you have those two things, if you have a model of both your business infrastructure as well as threat models, which can tell you mission and business impact analysis, look at my ability to do cause and effect mission impact analysis on the fly with a knowledge of the threat, a knowledge of the vulnerability, and now I can assess my risk based on threat and vulnerability. So this is really the future of the cloud and where it needs to go. I don't know of any other way to do it. And so now I could leverage the power of the cloud and its computation, its infinite scalability to both help me model these malware packages from binaries to my QML models. I can model threat, risk, and vulnerabilities. I can model my own architecture in the runtime and make all of this computable. Now I have a single computable paradigm for all three of these that create a superior view of both mission and business, but also make everything computable. And I think this is where it needs to go to move forward. And I'm looking forward to taking this on and making progress here within the next decade. Okay, so now the next step is, once you have the models, this is where we could really do the automation. And so if you can look at this as a ConOp or what we call a conceptual model, this is really everything that we need to harness. And so, automated risk analytics and threat surveillance is based on a combination of enterprise architecture views, but also target implementation and source code, and kind of storing these all in the same paradigm and making these computable. So once we're able to fuse these constructs of model-based systems engineering with AI, we feel that this is really the new plateau for securing the cloud. A lot of these constructs are included in the new SysML v2, which is now open on GitHub. SysML version 2 allows us to connect to UPDM and unified architecture frameworks, which defense systems and largely business systems are expressed in. So if I can describe my architecture, the systems, the data, the metadata, and the malware data all in the same paradigm, this allows us to both align our vulnerabilities to our architecture and our mission. It gives us a really enhanced ability to look at zero-day attacks and do that cause and effect mission impact analysis. It's more work up front, but in the long run, we feel that this would be a significant cost savings, because you can mitigate risk on the fly and have a tremendous amount more accuracy. And all this is required to get into the paradigm of real-time threat analytics and real-time countermeasures. You need an ability to model with granularity into a single construct. And so SysML v2, there's great hope. It took a while to get there, but there's great hope in what SysML v2 has to offer in this space. So this is an example of a threat surveillance model. As you can imagine, we've got the target, we've got our defense, we've got the attack, and then we've got our risk. And so all of these are important constructs to master when you're looking at concurrently running systems that do have codependencies, and creating models of these vectors, and having an observation threat surveillance model is really key. And happy to expand on this if we want to discuss it later. But this is really a lot of it's almost like playing golf. A lot of work has gone into this, it looks somewhat simple here, but this is a complex thing that through many years of research, we've kind of narrowed down into a single view. So my assessment is largely these, the COTS tools that are out there today are about 65% reliable. So that's, if you can imagine, there's still a gap there. We still have about 35% to eventually overcome. It's not insurmountable. I do think this 35% gap we can close in the next decade, and I hope I'm here 10 years from now to share the progress that we've made. And so this is what I think is the cloud of the future, and what it holds, and what it will look like. You'll have a repository to store, let's say malware observables, what we saw. We have an instrumentation layer. We have a services layer. We have an executable modeling layer. We have superior data management. We have characteristics and profiles of the threats and what we're looking for. And then we have an automated knowledge of our system in operations, which allows us to run computation against threat, risk, and vulnerabilities in the same paradigm. So this is really the end of my presentation. Happy to open up the discussion for any questions, and look forward to being with you in person next year.
All right. Thank you so much, Chris, for the great talk. Questions from the audience? Did I see something pop up virtually also? Okay. I thought you had a question. Okay, maybe let me start things off. So you mentioned that we have this 65% coverage with COTS security systems, and there's still the 35%. Do you have some anecdotes on what that 35% constitutes? I know a lot of this is unknown unknowns, right? But do we have a sense of where those are? What are those threats?
Yeah, so we have a real gap where we cross over our legacy architectures into some of our modern code packages. And so not only are there new packages coming online in exploits in large scale, but there are also many known exploits that we don't have an ability to always keep up with and mitigate. So there are a number of things, and largely our ability, we have a tremendous gap in our ability to compute mission and business risk and impact. So until we can have a real-time running cause and effect relationship and compute business and mission impact analysis, we're always going to have that gap of somewhere around 20 to 25%.
Hey, thank you so much. There was a question? Yes.
Hi, Chris. Okay. I have a small question. If you are constructing network models and anomaly models and malware models as per the current data, how does it continue to learn and identify newer patterns, which might be different from the current malware set?
Can you speak closer to the mic?
Hello. Hi, Chris. I have a small question.
Hi.
How does your network and anomaly models and the malware models kind of continue to learn so that they're able to identify the newer model or newer malwares, newer threats?
We can do this using scalable graph technology. So when we have and through active learning, so if we could look at a malware representation in a scalable graph, we can do a side-by-side view and look at what's changed over time. So we could run computation on the changes. We can run a query on as we write these changes into the database, we could run a query and ask it simple questions in natural language. What has changed in this malware package? And show us changes daily or weekly. And then you can slice and dice that data because it's written into the database with full granularity. So our ability to recall it is also as superior as the standardization we have when we write into the database.
Do you hear me now? Yeah, we want to thank you once again for the amazing talk. And just as a token of our gratitude, we're giving you this virtual gift card, Amazon gift card, as a token of our appreciation. Please do visit COMSNETS physically once the world sort of gets a little bit more kind, right, to travel. Thank you so much.
Thank you. Thank you so much. Thanks, everyone. Thank you, Dr. Mukherjee.
Yeah, and Dr. Supratik says hi.
So catch up on your sleep. I'll call you later.
Okay.
All right, I think next I'm going to hand things off to Rajesh for the remaining invited speakers.